Universal set, notation and symbolism. So we've started a new topic, notation and symbolism in set theory. And this first slide is an introduction to something called the universal set. Think of it like this. When we're working with sets, collections of things, we often need to define everything that's potentially under consideration. The universal set is exactly that. It's the set containing all possible elements relevant to the particular problem we're solving. It's the foundation upon which we build our understanding of other, smaller sets. This section, and the slides that will follow, will be dedicated to learning how we write about this universal set, using specific notation. We'll see how this notation is used in set theory equations. Those are just ways of expressing relationships between sets, and also how we can represent it visually using diagrams, specifically Venn diagrams, which we'll cover later. So, it's all about establishing a clear and consistent way to talk about and work with sets, starting with this fundamental concept of the universal set. Defining the universal set symbol. So let's move on to how we represent this universal set. As we discussed on the previous slide, the universal set is fundamental to understanding relationships between different sets. Now, to avoid writing out universal set repeatedly, mathematicians use a standard notation. The first point here states that the universal set is conventionally denoted by the capital letter U. So, whenever you see a capital U in set theory, you immediately know it refers to the universal set. This U acts as a shorthand. Imagine you're dealing with a very large collection of items, perhaps all the students in a school, or all the integers from 1 to 1,000. Instead of listing every single one each time, we simply use U to represent that entire collection. It allows us to write equations and perform operations much more efficiently. Now, this is a really important point to grasp. The specific elements within the universal set aren't fixed. They depend entirely on the problem you're trying to solve. Think of it like this. If we're talking about even numbers, our universal set might be all whole numbers. But if we're only interested in even numbers less than 10, then our universal set becomes a much smaller set. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So, always pay close attention to the context of the question to determine exactly what elements belong to U. This will become crucial when we start looking at things like subsets and complements, which we'll cover on the next slide, and also when we visualize these sets using Venn diagrams, as we'll see later on. Using the universal set in set theory equations. So let's move on to how we use the universal set, denoted by U, in actual set theory equations. First, we have subset notation. Imagine you have a set, let's call it A. If every single element within set A is also found inside our universal set U, then we say that A is a subset of U. We write this mathematically as A is a subset of U. Think of it like this. Everything in the smaller set A is contained within the larger set U. It means for every element X that belongs to A, that same X also belongs to U. Next, let's look at the complement of a set. Sometimes we want to talk about everything in U that is not in A. This is called the complement of A, and we denote it as a prime. That's A with a little apostrophe, or sometimes as A to the power of C. Mathematically, we define it as the set of all X, such that X is an element of U and X is not an element of A. Let's make that concrete with an example. Suppose our universal set U is the numbers 1 through 10, so 1, 2, 3, all the way up to 10. And let's say our set A contains the even numbers within that universal set, 2, 4, 6, and 8. The complement of A, a prime, would then be all the numbers in U that aren't in A. So that would be 1, 3, 5, 7, 9, and 10. See how it includes everything in U that wasn't already in A. Finally, we have union and intersection with the universal set. This is actually quite straightforward. If you take any set A and combine it with the universal set U, using the union operation, remember, union means everything from both sets, you'll just end up with the universal set U itself. So, a union U equals U. Similarly, if you find the intersection of A and U, meaning the elements that are in both sets, you'll simply get set A back. So, an intersection U equals A. This makes sense, right? Because U contains everything, taking the intersection with A just gives you A. These relationships are fundamental to working with sets, and we'll see how they come into play when we start looking at Venn diagrams on the next slide. Remember, understanding how U interacts with other sets is key to solving many set theory problems. Universal set in diagrams. So let's move on to how we see the universal set in action. This slide focuses on using diagrams, specifically Venn diagrams, to represent the universal set and other sets. As you recall from the previous slides, the universal set, denoted by the capital letter U, encompasses all the elements we're considering in a particular problem. Now, Venn diagrams give us a visual way to understand how different sets relate to each other, and crucially, to the universal set. The first key point here is that in a Venn diagram, the entire area enclosed by a rectangle represents the universal set. You think of the rectangle as the boundary of everything we're talking about. Everything inside that rectangle is part of our universal set. Now, other sets, like set A or any other set, are drawn within this rectangle. The way we draw them shows how they relate to you. If a set is entirely contained within the rectangle, it means all its elements are also elements of the universal set. Let's look at the example provided. We have a universal set, U, which contains the elements red, blue, green, and yellow, and we have a set A, which contains only red and blue. Imagine drawing a rectangle. That rectangle represents our universal set, U, and contains all four colors, red, blue, green, and yellow. Inside that rectangle, we draw a circle. This circle represents set A. Now, we place the elements of set A, red and blue, inside the circle. The area of the circle now visually represents all the elements that belong to set A. What about green and yellow? Well, they are part of our universal set, U, but they are not in set A, so they are located within the rectangle, but outside the circle. This diagram clearly demonstrates that green and yellow are elements of U, but they do not belong to A. This visual representation is incredibly helpful for understanding set relationships, especially when dealing with more complex problems. This is a crucial skill to master, as we'll be using Venn diagrams extensively when we start looking at operations like unions, intersections, and complements, which, as you've already learned, all rely on understanding the universal set. And remember, the next slide will recap all of this, so make sure you have a good grasp of these concepts. Key takeaways. Let's recap what we've learned about the universal set. This slide, titled Key Takeaways, summarizes the most important points. Next, it emphasizes that U represents the complete set of elements under consideration in a given context. This is really important. It's not just any random set, it's everything relevant to the specific problem you're trying to solve. Think of it as defining the boundaries of your mathematical world for that particular question. Moving on, the slide reminds us that the symbol U is used in set theory equations to define relationships between sets, like subsets and complements. We saw this in action earlier when we discussed how to write A as a subset of U, which we said as A is contained in U, and how to define the complement of everything in U that is not in A. So, U is fundamental to defining these connections. Finally, and this ties in nicely with what we'll explore further with diagrams, the universal set is represented by the enclosing rectangle in Venn diagrams. Remember, the rectangle is U, and all other sets are drawn inside it to show how they relate to the universal set. So, keep these 4 points in mind as we move forward. Understanding the universal set is crucial for working with set theory and visualizing relationships between sets using diagrams. Does that make sense? Common mistakes. This slide begins by pointing out that a frequent error students make is defining the universal set either too narrowly, meaning it doesn't include enough elements relevant to the problem, or too broadly, including elements that aren't needed. It's absolutely crucial, and I want to emphasize this, to carefully consider the context of the problem. Think about exactly what the question is asking you to work with. This will determine which elements should be included within our universal set, which we've been denoting as capital U. Let's look at an example to illustrate this. Suppose you're only discussing even numbers. In this case, a reasonable universal set might be all integers, that is, all whole numbers, both positive and negative, including 0. However, if the problem specifically asks you to consider even numbers less than 10, then your universal set becomes much more restricted. It would be the set containing 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Notice how we've narrowed it down to only those numbers less than 10. Finally, and this is a really important takeaway, always define your universal set clearly before you start doing any calculations or analysis. Writing down what your U is at the beginning will prevent confusion and errors later on. It's like laying the foundation for a building. A solid foundation ensures everything else is stable. Let's move on to the final slide, which highlights some common pitfalls to avoid when working with the universal set. So, you see how the context changes what we include in U? It's not a one-size-fits-all situation. By being mindful of these common mistakes and taking the time to define your universal set carefully, you'll be well on your way to mastering set theory.